Buonasera, signore e signori, e grazie mille al gruppo italiano Frattura for the invitation to talk to you this afternoon. It's indeed a pleasure to be back in Italy. I think when I was born there was a mistake. By inclination I'm an Italian. I like Italian clothes, Italian food, etc., etc. So probably I should be in Italy, not England. But I'm going to talk this afternoon about something that I think is quite interesting, but also quite complex. And that is, when Paul Paris proposed his stress intensity factor, it is an approximation to a global elastic field. And his papers were turned down because the theory was, how can an elastic parameter deal with what is known to be a plastic phenomenon, which fatigue is? And that remains the problem. Although K works fairly well to characterize approximately the elastic field, at the local level around the crack, which reflects the plastic deformation mechanisms of crack growth, there are problems. And so this talk is about a new approach to dealing with plasticity-induced crack tip shielding. And my co-authors are my PhD student, a mathematician at Plymouth, and Professor Ian Patterson, who was head of school at Michigan State and is now director of Composite Vehicle Research Center. So the talk outline is this. Background. Why are we interested in a multiparameter approach to crack tip stresses? The model, which is a Mashkelishvili complex potential extension to Williams crack tip stress field for 4 stress parameters. And then some experimental verification via full field fitting, and we can do this either for photoelastic or for strain through digital image correlation. And we've applied this so far to fatigue crack growth in polycarbonate at various stress ratios and with an overload. And at that point there are issues around, is polycarbonate a decent model material? And then some conclusions. So background. As I said, the single parameter approach to crack tip stresses has been very useful. We can characterize fatigue crack growth, and it really underpins the simple development of defect-tolerant approaches to life prediction. And you can modify this, and this was done in the 1970s, to account for the plastic wake that fatigue crack growth, or indeed fracture, has necessarily attended on crack growth. And you do that via this delta K effective. But that's not straightforward. And there has been controversy around plasticity-induced shielding, about the mechanisms, magnitudes, and measurement. And to date, we do not have a full understanding of the plasticity-induced shielding phenomenon. And so the question must be asked, is a single parameter approach sufficient to describe crack tip effects? And if not, how many parameters do you need? And quite a lot of work recently has been looking at K plus T. And so it's become clear that the extent and shape of crack tip plasticity is affected by the T stress. The T stress is the second term in the Williams expansion. It's non-singular, which means it has a fairly constant value. And it's under small-scale yielding conditions, the T stress describes the effects of geometry in plane and loading type, e.g. tension versus bend, on plastic deformation around the crack tip. And so a lot of people said, okay, we cannot ignore T, and this is true. Another work, using 3D finite element analysis, has indicated that T stress influences the closure process, in other words, the shielding process, through 2 factors: the stationary crack opening displacement and the residual plastic deformation of the wake. And other works demonstrate a strong influence of T stress on crack front stresses and deformation fields. And so what we know is that the size of the near-tip plastic zone increases as the T stress deviates from 0. So the T stress has an influence on plasticity around the crack, and therefore we need to consider the T stress. And negative T stress causes the plastic zone to spread ahead of the crack tip, and positive T stress causes it to tilt backwards. And again, positive and negative tend to reflect the specimen type as well as the loading. So a compact tension specimen has a different T stress to a center crack tension specimen. Now here are some images that are actually generated using our model, which is a 4-parameter model, but we can model T stress, K stress, and the various shielding stresses. But what this indicates is These are fringe patterns of difference of principal stress. So they're directly analogous with photoelastic images. What happens if we have increasingly positive T-stress? And you can see that as the T-stress gets more positive, the fringes tilt backwards. And this is an increasingly negative T-stress from left to right. And you can see they start to tilt forwards slightly. And in fact, the mathematician I'm working with has a neat model where you can put virtual fatigue cycles on and get fringe patterns of difference of principal stresses out and change the parameters. So you can apply virtual fatigue cycles and see what the fringe patterns look like. And just to emphasize this point, this is a variation of second order fringe of difference of principal stresses and shape of the T-stress using our model. And that's +2, +4, +5 megapascals positive, and negative it starts to be like that. So what we know now then is that the two-parameter approach of using stress intensity factor and T-stress can capture influences of the applied elastic field on the local plastic deformation. What we're not able to do yet is really account for any influences on the applied elastic field of this plastic zone around the crack tip. That remains the complex bit. And if you say, well, let's just do K max minus K minimum, in other words, delta K effective, you are not capturing those effects properly. And that's well known because lots of work has shown that the range of effective delta K is different to K max minus K minimum. So if you look at the mathematics, some time ago, Eshelby, who was really quite a decent mathematician and dislocation specialist, proposed the concept of plastic inclusion as a mathematical approach to dealing with composite materials. Now in this context, composite means part of the material has undergone instantaneous change in properties. So what he was talking about was either a phase transform zone or a region of plasticity. Now it turns out the mathematics of dealing with Eshelby inclusions is not straightforward, but is possibly or probably feasible. But you would anticipate that the influences of such a plastic inclusion would include the well-known fracture surface contact, crack closure, and indeed there has to be, something that's been ignored up to now I think, compatibility-induced shear stresses at the elastic plastic boundary. And those have to happen because plastic deformation is a constant volume process with Poisson's ratio 0.5, whereas elastic deformation has a lower Poisson's ratio. And as I said, that's moderately complex, but I think we might be able to do it. But as a first step in seeing whether we can move forwards with the concept of a plastic inclusion, we have proposed a crack tip stress model that incorporates, well, we hope realistic, assumed influences of the plastic enclave. And so what we're trying to do is capture effects of the crack tip and crack wake plastic enclave through elastic stress distributions applied at the elastic plastic boundary. And that is quite useful because it means we can ignore details of plastic deformation. It's also quite useful because when you use photoelasticity, you have to mask out the plastically deformed region. And what you can get is stress or strain fringe patterns directly comparable with either photo-E or digital image correlation, i.e. strain. Now the model is relatively complex mathematically, although I must say it takes the mathematician very little time to do this. The first time we tried to do it, it took an engineering postdoc 3 years, but the mathematician apparently can do this in half an hour. So that's the difference if you get a mathematician involved. So as an extension to the crack tip stress field, what we say is we take the Williams expansion for stresses, but we have a K stress, a T stress, a weight contact stress, which we model as a distribution decaying with R to the -half dependence, acting along the crack flank. So that is the crack contact. And you can take that off at various points in the load cycle, and a compatibility-induced shear stress at the elastic plastic boundary. And we've validated the model via full field fitting, and we've extended it to strain fields. We've solved the equation for DIC, and therefore we can now start to deal with metallic alloys, which are far more interesting than polycarbonate. So we have got in the photoelastic work isochromatic fringe patterns giving lines along which principal stress difference equal to constant. And we can solve the stress equation to provide that, and that allows a direct comparison to be made between full field photoelastic patterns and mathematically derived full field fringes. And the photoelasticity is not simple, but that's been the contribution of Ian Patterson. So values of constants in the theoretical equation can be obtained, and the area and the fit can be calculated. Now this is the final equation that we have developed, and it is, as all things are, a step in the process towards what may be the truth, but we hope it is a step forwards. N is the photoelastic fringe order number. F is a material fringe constant, typically rather small for polycarbonate, unfortunately. That's the specimen thickness. Now the terms in z to the minus half model the K stress, and the terms in z to the 0 models the T stress, and the other terms describe a crack retardation stress and a compatibility-induced interfacial shear stress. And you have to have specific conditions applied at constants to give the appropriate form of the stress distributions. But you can then interpret these three stresses as a net tensile stress perpendicular to the crack, a net direct stress acting parallel to the crack, and a net shear stress. But each of these three stress components include effects of the elastic plastic boundary, and they now take into account the total plastic enclave, the crack wake, as well as the crack tip plastic zone. So in principle, what we're trying to do is fairly straightforward. And we're trying to extend the linear elastic stress intensity concept to account for known influences of the plastic enclave generated by fatigue crack growth. And we think that it captures some key attributes underlying the dichotomy of using a global elastic stress parameter to characterize the crack growth phenomenon based on local plasticity. That was why Paul Paris's papers were rejected, and that remains a slightly problematic issue. And so what we've then done, and this is where we're not fully sure whether we have the right terms or not, we have defined three stress intensity factors using the three stress components. And we can interpret these in terms of their effects on the growing fatigue crack, and we can hopefully determine the correctness of our assumptions from their capability in characterizing or predicting fatigue phenomena. And so you end up with these three stress intensity factors, where Kf now is a driving force for crack growth. That's why we call it F. It's a forwards force, a driving force. It includes a contribution to direct stresses in the y direction arising from shielding and reflects Poisson's ratio influences and compatibility with the elastic plastic boundary. So it is slightly different to the traditional K, but acts in the same direction. We have then defined what we've termed Kr, a retarding stress, which characterizes the direct stress opposing or retarding the crack growth parallel to the plane of the crack. And that arises primarily from the plastic zone, plastic enclave around the crack. And it does include, so the mathematician tells me, influences of weight contact stresses, because at the crack boundary, sigma x and sigma y are equal in magnitude. And so that picks up the shielding from the crack closure and the Poisson's ratio effects on the plastic zone. And then lastly we have a Ks, which is a shear-induced stress intensity term, and it reflects again the compatibility-induced interfacial shear stress of the elastic plastic boundary. And you can then model the near-tip principal stresses for each of these terms acting in isolation just to see does it look reasonable. This is Kr acting alone at zero applied stress. Blue is compression, red is tension. This is non-dimensional. Mathematicians love non-dimensional figures, and the difficulty we face is getting them to actually dimensionalize them in terms of real stresses and real specimen dimensions. But nonetheless, you can see that this is Kr's effect, and that's the principal stress. We can then resolve into sigma y and sigma x. And so this is sigma y, the stress perpendicular to the crack. For Kf, the forward stress intensity factor, equivalent to K, the normal K1, greater than 0. And this is sigma y for Kr negative. And although there might be argument that you can't have negative Ks, mathematically, of course, you can. So that's fine. So that's the model. It's a little complex, but not too complex, and I'm hoping the mathematician will now solve explicitly the Eshelby plastic inclusion, because that should tell us whether we've got the boundary conditions on the plastic zone right or wrong. So now on to the experimental verification. Well, so far we've tried digital image correlation, and we've mainly tried photoelasticity. We've looked at 2 mm thick compact tension specimens of polycarbonate. That's what they look like. Now, polycarbonate's a good material. It's birefringent. It has continuum fatigue crack growth mechanisms over a range of crack growth rates, which is useful if you're trying to model continuum plasticity. And it has ductile crack tip deformation by crazing, which is analogous to the Dugdale strip yield plastic zone model. And there is the plastic zone running along the crack in a photoelastic image. Now, the other thing about photoelasticity is you can see explicitly, only just, I must be honest, the effect of the shielding. This is a fatigue crack grown from a notch, and this is at zero load. This is K value. This is normal K1 value. You'll see that that increases. If you watch these fringes carefully, you will see that energy is released during the early part of the fatigue crack growth, during the cycle. So as the load increases, energy is released, which implies you have a shielding phenomenon, and then you'll see they start to expand. So you get a direct view here, and it's a very local view. And so we are hoping that by getting this fit right in the model and the theory, that we're picking up these local plastic effects. But you have to look very carefully. So K is going up. These are in fact decreasing if you look at them very carefully. And then around about now, they start to expand. And so during the first part of the cycle, energy is being released as you take off the residual stress effects of the plastic deformation. And why the student didn't carry on to a higher value of K, I don't know. Students do random things. So if you watch that again, perhaps, it is clear on a computer screen. You will see that the fringes are contracting. So it's quite a nice model material, polycarbonate. We've had many discussions with referees over the years about the model, about why we don't consider plastic deformation mechanisms, about whether polycarbonate shows continuum plasticity or not. And I think we've put most of the arguments to bed, but not without interest. So the photoelastic analysis is relatively complex, but it's now computerized and straightforward. It's a phase stepping technique. We mask the regions surrounding the crack where plasticity is present. We have explored the effect of that masking region on the results. And we therefore need to know the size of the plastic region, and we can do this via a Dugdale equation. But we can also directly visualize the plastic zone around the crack using confocal laser scanning microscopy via the change in refractive index in the craze. When you develop a craze, you void the material. Voids develop in the craze. And in fact, this then changes the refractive index. And the net effect is if you rotate this image to be in that orientation, you will see that the change in refractive index has apparently lifted the plastic zone out of the material. So interestingly, confocal laser scanning microscopy gives you direct visualization of plastic zones in PC. So we're going to write a PC paper at some point to show. So the other thing is that it turns out that the confocal laser scanning microscope, if you scan through the thickness of the specimen, you get an interference phenomenon known as Fizeau fringes, which is sum of principal strains. And for the mathematician to solve the model for sum of principal strains, it's fairly straightforward. It takes him 10 minutes instead of half an hour. And if you look at the fringe pattern here, again, this is non-dimensionally present, but that is the model equivalent using our model of the fringe pattern shown there. And then these bits going back here apparently show the effect of a shear stress, which we haven't adequately got in that yet. So if you do the full field comparison, we've taken the photoelastic isoclinic fringe pattern, difference of principal stresses, and we've looked at, in fact, compared our solution with the four stress parameters with the standard Williams solution taking out K and T. So figure A is the Williams solution with K and T. Red are the theoretical fringes, blue are the experimental, and this B over here is the new model with four stress parameters. Now the fit may not look too different, but in fact if you look at the error here is a good 30% lower in the key area around the crack tip than that one. So I'm not saying this model is totally right yet, but it's on the right track. And you can then have a look through using real fatigue crack growth and polycarbonate. This is the sort of data you get out. This is the two stress ratios. This is a crack length of 35 millimeters, a stress ratio of 0.1, Pmax 120 newtons, equivalent to a Kmax of 2.07. And you'll see that the Kf, which remember is equivalent to K1, does this and follows that. That is the line of K1. Kr does that, and Ks does that. And if you move up to R.5, you get different values. So we are capturing differences in the fatigue in the plastic zone arising from the difference in stress ratio. So that makes one feel fairly positive, at least you have something that's possibly realistic. So the conclusions are that this new approach apparently gives a better fit between the model and experimental data than you find using K and T. Improvements believed to reflect better capture of local effects associated with crack tip plasticity and crack weight plasticity. And we apparently get sensible trends for Kf, Kr, and Ks and T stress as a function of crack length, stress ratio R, and indeed in the presence of an overload. So this is work in progress, but it is trying to say K doesn't work, why it doesn't work because of local plasticity, how can we make it work better, and we're trying to do that. So thank you for your attention.